Hi, welcome to Lecture 13, Lucky 13. Um, we're going to be going through two sections of the GIM book today, 2.6 and 2.7, which will bring us to the end of the chapter on logic, and then we'll begin our first exploration of actually doing real proofs. Well, we've actually done a few real proofs. I shouldn't be that cavalier about it, but anyway, we'll be moving on. So here's the layout of what we're going to do today. First, we'll talk about what constitutes an argument in logic, not the sort of argument where people are threatening one another with fists or whatever. We'll go through a fairly lengthy list of the rules of inference. So we'll start off with some sort of general comments about why we have these rules of inference and a particular type of the rules of a type of inference rule is a thing known as a syllogism. So there's a couple of syllogisms we'll look at in great detail, and then we'll in the midst of that syllogism section, we'll actually show how to establish that one of these rules of inference is correct. Finally, we'll end with a couple of mistaken argument forms that people make, and I think we'll easily see why they're wrong. So it's sort of like know your enemy, right? If you know this sort of error is there, then it's easier to arm yourself against making that sort of error. All right, so first, arguments in general. There's basically two styles of argumentation that people make. We're going to look at deduction for the most part, but frankly, induction is what is more natural for human beings. We evolved as animals in a world that has a lot of hazards in it, right? And the process of induction is a good one for protecting us from those hazards. We learn inductively to avoid things that are dangerous, and deduction is less natural. Well, anyway, induction is basically about seeing patterns, seeing the same phenomenon occur again and again, and coming to the conclusion that that pattern will continue. Imagine some caveman saying this. Well, maybe not saying this because this isn't English, but you know what I mean. I've eaten those red berries many times, and I've always been sick afterwards. And Grog thinks for a while and goes, "I shouldn't eat the red berries." That's induction. Seeing a bunch of examples. Gee, every time I ate those, I got sick. And then realizing you have a conclusion to make. So deduction is less natural. We actually need to learn it. It's not something that comes to our minds easily. What's the example? Oh, well, first, what is it about? I like to think of it this way. You think about the consequences of an action, and then realize that the consequences have consequences. And then you chain those together until you reach a final consequence, possibly something you want to avoid. So you say, well, let's not get that started. Don't make the first thing happen. And so here's an example. The badger has sharp claws and teeth. Sharp claws and teeth will not feel good on my face. If I poke the badger with this stick, I shouldn't poke the badger, should I? Yeah. So this is kind of a silly non sequitur, but I always, when I'm teaching this material, and sometimes I teach this in discrete math, but also in these intro to proofs courses, I like to show students this thing called the argument clinic. It's a sketch from the comedy troupe Monty Python's Flying Circus. To modernize, this will look really kind of cheesy and hackneyed, but it was honestly avant-garde comedy when it came out in the 60s. Some of the actors in the Monty Python troupe continued on to great success in film, and one of them became a pretty successful director of movies. So, well, I didn't mean to click on that thing, so I just backed up a little bit and took it away. The link, though, is right here to that argument clinic sketch, and it's funny. Take a second and check it out. The main reason I'm suggesting to you to check it out is this. At one point in this sketch, one of the participants is trying to convince, they're, it's too weird, never mind. One of them makes this sentence: an argument is a connected series of statements designed to establish a definite proposition. And this is in the midst of just, ridiculous back and forth between the two characters. And suddenly he says this completely lucid and basically exactly correct definition of what an argument is. And I do mean the logic and philosophy style of arguments, not the kind you have in sports. I think it tells us that the Monty Python gentlemen it was an all male troupe, I believe. They must have had a really good education. They had actual training in rhetoric and logic, because where else would you get that? This was comedy that was released before the internet existed. You couldn't just Google it. Okay, so we're going to try to focus on arguing convincingly. I believe I've made this point before, that an argument, a proof, is nothing more than a convincing argument that's done in a certain formal way. So we need to argue well. And in fact, you can take these skills in argumentation and put them in the real world as well. Not necessarily doing mathematical proofs, but ordinary human discourse, the ordinary human process of trying to convince somebody that you're right and they're wrong. The training that math majors get in this process of arguing convincingly is one of the reasons, I think, that math majors are sought after in law school. So a really good undergraduate degree to get if you want to go into law school is math. Strange, because quite honestly, the law doesn't have very much to do with math, but it does have to do with arguing, and mathematicians, and we learn to argue well. So yeah, an argument is just a collection of statements, true or usually true statements, we hope. There are three kinds, and these are normally separated out. First, you'll see hypotheses. What's a hypothesis? They're statements that you treat as definitely true, at least in the current situation, the arena in which you're making the current argument. You should know that these hypotheses hold. Then there'll be deductions. And what are deductions? Well, they're the statements that you can infer or deduce from the statements that came before them. So I guess your first deduction has to just be deduced from the hypotheses. Later on, you can start using previous deductions. So, but everything that you write down has to follow from the stuff above it in the argument. And then conclusion. That's the goal. That's the thing you are trying to prove. Let's see. The conclusion is the whole point of the argument. That's right. You're trying to establish the truth of this particular definite proposition. And that's what the connected series of statements was designed for. It's supposed to establish that proposition. It's important to notice the conclusion, not important so much, but you don't want to be confused about the status of this. The conclusion is also a deduction, right? You're deducing something from the things that went before. It's the end of the train. It's the one where you go, okay, fine, we got where we wanted to be. So rules of inference is our next section. What are they? Or what is inference? It's really just another name for deducing, making a deduction. So infer and deduce are synonyms. They have the same exact denotation. They connote things slightly differently. I believe people usually think we infer things in an informal, maybe intuitive way, whereas we deduce, that means you're applying logic. But the literal meaning is to take some true statements and get new true statements from them. So what are the rules of inference? They're a fairly small collection of, I call them mini arguments. They give us a formal scheme for this process of getting the next line in an argument. The things that have to follow from stuff above. A mini argument will list a couple of the things that are above and then let you figure out what you can deduce from that. That's a fair way to put it. They're the glue that holds our argument together. So here's a practically trivial example of one of the rules of inference. It's called conjunctive simplification, and it's this. If you have the statement A and B, you can deduce from that the statement A. That's definitely not rocket science, right? You know that A and B are both true, so you go, okay, well, A is true, and just forget about B. I could have just as well said B is true, but that would be the same thing. Just that would just be a change in the names of things. So I'm mostly putting this guy up here to give you an idea of how the format should look. For when one of these rules of inference, you're going to have several lines, in this case just one, but a bunch of lines that appear on separate lines above a horizontal line, and then the symbol with the three dots, a triangle of dots. That stands for the word therefore. And then the conclusion also, and the therefore and the conclusion are going to be below that horizontal line. So do you see how the conjunctive simplification looks? We've got a hypothesis, and then we've got, that's the end of the hypotheses, and we conclude with therefore and A. Conjunctive, I said this already. There often are more. There are often, in fact, usually there's more than just a single hypothesis. Two, sometimes three or four even. Disjunctive addition is another one that has a single hypothesis. Let's look at that one briefly. It's the only hypothesis is some statement A, and then the conclusion we draw from that is that A or B. In other words, if A is true, then we can deduce that A or B is true. And it doesn't even matter what B is, right? We can throw anything there because this or sentence is going to be true when the thing on the left side is true. And our hypothesis is that it is true. So those are pretty lame, I admit. They're just there to give you some examples of what a rule of inference could be. But I will actually tell you this occasionally happens that you need these sort of seemingly trivial ones. So don't ignore them. They occasionally pop up. All right, so syllogisms is our next thing to tackle. What is a syllogism? Basically, it's one of these mini arguments where there's exactly two hypotheses, so two lines above the line, two statements above the line, and then a single conclusion. There's always just one conclusion. Quite a few of the rules of inference are syllogisms. That's true. And we actually talked about this one before. This is a syllogistic form. All men are mortal. Socrates is a man, therefore Socrates is immortal. I have to be careful how I pronounce that. I don't want it to sound like immortal. Socrates is a mortal. Okay, so this is our first rule of inference. That's not one of those sort of too easy type. Modus ponens. That's actually it should be Greek, but that's Latin. Modus ponens, the method of affirming. It's the generalization of that argument about Socrates. The first line in the argument about Socrates is all men are mortal, but aside from the implicit sexism in that, it's not clear, I think, to people that that first line is an if-then. So think of it this way. If X is a human, then X is mortal. Same content, right? All right, so we've got an if-then sentence. Humanity implies mortality. Socrates is human, therefore Socrates is mortal. So making it abstract, it looks like this. You'll have a conditional, A implies B. The A was humanity, the B was mortality. Right? Socrates is human. That's our A part, about Socrates in particular. And then our B part is that Socrates is mortal. Some terminology. The conditional in that modus ponens argument form is called the major premise. So one of the things that will occasionally happen is somebody argues with perfect logic, but working from a false major premise. And then everything is awful, right? If you have a false major premise, then your conclusion is not going to be true, or not necessarily true. It could accidentally be true, but arguing from false hypotheses is a real bad thing. When you do such a thing, the argument is known as, let's see, we have validity and soundness. It would be an unsound argument when you have a false major premise. Anyway, the other hypothesis is called the minor premise. I guess that makes sense, major and minor. There are variants of these, and more terminology we need to learn, that have to do with how you quantify things. So the three variants that you'll see are modus ponens, universal modus ponens, and the particular form of universal modus ponens. Actually, that Socrates argument is, I was trying to be cute here, PFUMP, particular form of universal modus ponens. So that looks like so. You'll have a universally quantified conditional. That is, the major premise is universally quantified. We've got, instead of A and B, we have open sentences, A of X and B of X. And there, A of X implies B of X for all X in whatever universe we're in. Didn't say this up front, but U is very typically used as the universe when you don't really know what the universe is. Oh, okay, but it's the particular form. So the next line, A of P, that's not about there's no quantifier on it. A of P is a particular element of our universe. Now, I just want to point out this parenthetical remark is there just to tell you what I just said in words. It's not part of the argument form. Right? So if you imagine that with the parenthetical remark just removed, that would probably be good. Yeah, so what else do I have to say? If it's always the case that A implies B, and A is true for this particular dude, then B is going to be true for that particular guy too. If you're going to look at the full-on universal modus ponens, it's well, first of all, it's less common. It's substantially less common, in my opinion, because think about what the hypotheses are saying. Well, let's look at it first, and then think about what the hypotheses are saying. Everybody's universally quantified. That's why it's full-on universal modus ponens. So we've got the if-then, A of X implies B of, sorry, bad highlighting. A of X implies B of X, universally quantified. All X make this true. It's also universally true that A of X rather is true. And so universally we can conclude that B of X is true. That's a lot of oomph, right? The hypotheses are strong statements, and they the thing we deduce from them is a very powerful statement. It's not that common that we have so much potency to work with. So you will see this less often than the particular form. Do you guys know the saying "trust but verify" in the title of the slides? Something that Ronald Reagan said about the former Soviet Union back when it wasn't former. He was talking about arms limitations treaties. So we need to verify these rules. I mean, you should trust me that I'm not lying to you. These are valid rules we've talked about, or we're going to talk about. But we should definitely check them out ourselves to, be sort of ethical mathematicians. We need to know that the things we're working with are valid. There's essentially two ways you can do it. Using a truth table is sort of my favorite, to be honest, because it's direct and it's a simple way to proceed, and you get a good result. So we're going to come back to that. The other thing you can do is show that the rule of inference is equivalent to a tautology. And let me give you an example of this using modus ponens. So first off, this is how you could re-express modus ponens all in one line. You see, the two hypotheses are A implies B and A. And what we want is that if both hypotheses are true, that should imply that the conclusion of that little argument is true. So if we put an "and" between the two hypotheses, the two of those things together, "anded" together, will imply the conclusion. So I've just written the modus ponens rule as a single line sentence. Can you verify that that is tautological? Yeah, it's a task. Let me tell you, it's not terribly, well, it's not super challenging, but it's definitely takes a little work. So I worked it out in advance, and I'm going to do one of those things where we'll reveal things a little at a time, although it looks to me like you can almost see through the paper amusing. So there's your first line, which is the sentence I gave. A implies B and A implies B. All right, so the first thing I'm doing is re-expressing the conditional that's on the inside. See the A implies B right here? Re-expressing that with the equivalent disjunction, not A or B, and then everything else remains the same. There's the statement where I have, well, the next thing I've done to it is replace the second implication with the equivalent disjunction. So the whole thing on the front of the if then has got a not on it, and then the thing to the right of the if then has been kind of redrawn unchanged, and we changed the operation to or. So this is like not A or B, except the A has some structure to it. Great, so let's go one more. Well, I need to negate that thing that's on the left, so that's an application of De Morgan's law. We're negating an and statement, really. The first half of that and statement has some inner complexity, but it's the stuff that's in parentheses. The second half is just A. So I put the not on both pieces, and I turn the operator from an or to, from an and to an or. And then the or B part on the end unchanged from what's above. Then I screwed up when I was doing this, and I just didn't feel like redoing it, so you'll have to live with that I scratched it out and replaced it. What I was trying to do next was, again, applying De Morgan's law, distributing this not into the disjunction that's right here. And what I did is accidentally wrote a disjunction again. We know that if you apply De Morgan's law, the symbol's supposed to change. It's just a braino. So that's supposed to be an and in between them. I also did a little bit of a cheat here in that we really would have the not of A, and I just went ahead and wrote A. So the double negation, I just elided the step where that gets simplified to simply A. So this should be A and not B, ORed with not A, ORed with B. What happened there? This is a good challenge for you. Can you tell what happened? Because I didn't actually make a two-column proof. I don't have the second column with the explanations. But I know what happened. So has anybody, have you seen it yet? This is distribution. This not A is distributing into the conjunction next to it from the right. So this is the right-hand version of distribution of disjunction over conjunction. We end up with a couple of disjunctions, A or not A, anded with not B or not A. The not A has shown up in front of the not B as, behind the not B, and also behind the A with an and in between them. And then the or B just got carried down. We're getting close. Seems like a lot of work, doesn't it? A or not A is a tautology, so we can replace that with a T. And then a tautology anded with somebody, that's the identity, right? The and of something that's always true with some other guy just takes on the truth value of that other guy. So we just get not B or not A here. We still have to or it with B, so that's still to be done. I just commuted them. That's all that happened on that line. I just switched not A and not B inside the parentheses. Why did I do that? Well, you might see why I did that in the next line. So I could re-parenthesize using the associative law and get that not B and that B together. Why? Because that's a tautology. So we have not A ORed with a tautology. And finally, the dominance law applies, because if you have an or statement and one side of it's true, the whole thing is true. So we did, I don't know how many steps this was, like a dozen. But we did show that that sentence right there is tautological. Painful, but we got there. Well, I don't know. Was it painful? I think sometimes it's actually kind of amusing to try to work your way through one of those things. All right. The truth table approach. Let me just say what it is first. You construct a truth table and you want to create columns for all of the statements in the argument you're analyzing. So all the hypotheses together with the conclusion. You're going to mark in some fashion all the rows where every single hypothesis is true. All the hypotheses need to be true. Those are called critical rows. So just indicate them, or else cross off the ones that aren't critical, maybe. I don't know. You only want to really be looking at these critical rows, because the point is that the conclusion needs to be true in those critical rows. When the hypotheses are true, we need that the conclusion is true. This would not be a valid argument if sometimes all the prerequisites were satisfied and you didn't get your conclusion. So we're going to use that approach on our next syllogism, but let's look at the next syllogism first. This one's called modus tallens. In Greek, that means the method of denial. There's actually a fuller name for both of these. You could have modus tollendo tollens, which means the method of denying by denying. And there's also modus ponendo ponens, the method of affirming by affirming. I'm not quite sure why the full-on Latin has such a redundancy in it, but it sounds kind of funny. Anyway, modus ponens is also known in sort of standard English as the method of affirming. I personally say the method of affirmation, denial and affirmation. So the modus tollens rule has the same major premise as modus ponens. You'll start with a conditional A implies B. And let's look at the particular form of universal modus tollens, just to be concrete. You've got a universally quantified conditional sentence up at the top. For all x in U, A of x implies B of x. Then we have the negation of B applied to some particular thing in their universe. And we conclude from those two the negation of A for a particular thing in the universe. Make sure that you recognize you need a not, and you also have to be the not of the second thing in your conditional. So that rule is valid. Let's do it, and let's do it by a truth table. So I pre-prepared a truth table for us to fill out. Let's see how this works. About here, I guess. So we've got columns first for A and B. So that's just the setup of the truth table. But then we have a column for A implies B and a column for not B. Those are the two hypotheses. Excuse me. And then here's the conclusion, not A. Now, I put these sort of double lines into here to separate things. The hypotheses are the ones between the two sets of double lines. The conclusion is up there on the right by itself. So let's get busy and do this thing. The first thing is to just fill in the usual pattern of trues and falses on the input variables. I guess I didn't make the lines quite long enough. All right, A implies B. That one's easy. We've done that a million times. It's false in row 2, right? False right here. True for good reasons upstairs and true for vacuous reasons in rows 3 and 4. Now, not B is also relatively easy. It's just the exact opposite of whatever B is. So when B is true, it's false. This has a true, false pattern. This guy has it alternating in the other order, though. False, true, false, true. And actually, similarly, not A is pretty easy to do. It's false in the top 2 rows and true in the bottom 2 rows. So where are the critical rows? Well, perhaps I shouldn't say rows plural like that, because there's really only one. The two premises, A implies B and not B, are only both true in this row. and our conclusion is true in that row. So in the one scenario out of all of them that comes up, where both the implication, the conditional, and not B are both true, not A is true. That means you can deduce from the truth of the first two that not A is true. The final thing, the conclusion is true. That's verifying a thing using a truth table. That to me seemed like considerably less work than this. Just saying. Maybe some truth tables versions of more complicated arguments would be as difficult, but I don't know. I'm not sure how that's going to play out. I would make sure that you can do it both ways, because you're taking a class right now on this, and so one of the things that might show up is a test question that says verify this rule of inference by showing that it's equivalent to a tautology. If they give you instructions like that, you got to do it that way. I might get partial credit if you showed me a truth table, but I certainly wouldn't give full credit. I don't know what other professors might do. All right, so there we go. So there is a link to a handout in the video description, and I have a copy of that handout available for us here. This is one of the tables from the chapter in GIAM that we're working on right now. In the book, this is typeset so that it's big, and it had to be on two pages, facing pages. So I shrunk it a little bit and managed to get it onto a single sheet of paper in landscape mode. So here's all of them. It's not that many, right? And actually, several of them we already know. Modus ponens and modus tallens. We've talked about them fairly much at this point. There was a couple of other ones that we already talked about. Conjunctive simplification, that if you have A and B, you can just forget about B and get A. And also disjunctive addition. If you know A is true, then you can OR it with anything else, and that'll be true too. Okay, so we've got 1, 2, 3, 4 of these done. How many are there? There's 10. So we're halfway. Okay. I'm not going to cover them all, though. I like this next one a lot, hypothetical syllogism. And mostly I like its name. That's a cool name. Hypothetical syllogism. The point is that these are hypotheses. These are hypotheticals. A implies B and B implies C. From that, you can conclude that A implies C. I think that's very nearly the example I gave of the caveman thinking about poking a badger, right? If I poke the badger will bite me. If the badger bites me, it's going to mar my face, and the cave women won't like me. Therefore, what do you get? Oh man, I confused myself. If we poke the badger, we'll end up ugly, right? I've got a bug in the house. Weirdness of working from home. So that rule actually makes sense, doesn't it? It's sort of a transitive property of the implication arrow. Disjunctive syllogism. You could actually recast this by turning the A or B that's there up front and turning it into the equivalent implication or the equivalent conditional. And you'd find that you're really just looking at either modus ponens or modus tollens. But it's often enough we see this that you go ahead and use it as it stands. So the first line says either A is true or B is true. The second line says B isn't. So one of the others is true, but it's not the second guy. Well, it must be the first one. So we can conclude that A is true from these two sentences. The next couple of things are dilemmas. In ordinary language, a dilemma is when you have a sort of a difficult choice, maybe an impossible choice. In the book, there's a version of a dilemma that's given. It's called the crocodile's dilemma, which is a little bit macabre. But I'll give you an example from very old school comedy. There used to be a comedian whose name was Jack Benny, and part of his shtick was he would pretend to be really cheap. Apparently, people who actually waited on Jack Benny said he was quite the opposite. He was a great tipper, but Anyway, it was his deal. He pretended like he was a real cheapskate. And so one skit he does where there's a guy comes running up to him and he's got a gun and he gets in his face and yells, "Your money or your life?" And Jack Benny goes, he's just sitting there. And finally the guy says, what are you going to do? Your money or your life? And he goes, I'm thinking. I can't do a good Jack Benny imitation, but that's the gist of it. That's a dilemma for him because he's so cheap that dying or losing his money, what should he choose? I only mentioned that because the word dilemma is used in a different way here in logic. We have these two implications that end up, and then additionally an or statement that gives us another or. The reason these are often called dilemmas is because it's very common that the second pair of things, the B and the D, are the same. And so it's sort of like saying two routes that lead to a final conclusion. If B and D were equal to one another, then this final line here, B or D, would just be whatever they're equal. Let's call them B. All right, so we'd have A goes to B and C goes to B. A or C is true, therefore B is true. It's two different paths getting us to B. And that's the die part of the dilemma, I think. At least that's the way I understand it. The second one, I'm not going to go over too much because you can realize that it is essentially the same thing as the first one, except the statements have been replaced with their contrapositives. If instead of A implies B, you had not B implies not A, not B would be on the left, right? And it would be one of the things. I call this putting it through the contrapositive ringer, basically. If you think about how constructive dilemma changes when you replace the conditionals with their contrapositives, you get destructive dilemma. That same thing is true, by the way, for modus ponens and modus tallens. If you just replace the A implies B with not B implies not A, and change names, you end up with modus tallens. So these two are related by the contrapositive, and these two are related by the contrapositive. Conjunctive addition is one that we haven't done yet, but look, it's just saying that both A and B are hypotheses. If they're amongst the hypotheses, we know they're both true. So the statement A and B is true. That's again one of these sort of almost too easy things like the conjunctive simplification and the disjunctive addition. Finally, we've got a rule called absorption, and I'm not going to cover it. You can do what we did, form a truth table, and there's only two variables, so again, it'll just be a 4-row truth table. See when the two things are true. It's called absorption, and that's actually what I'd like to focus on because I honestly don't know why it's called absorption. So if any of you can figure out why that's called absorption, put something in the comments so that I know. That would be really awesome help. Okay, we're done with the rules of inference. That was literally a whirlwind tour, but you'll have this handout, and when you're first doing proofs, you might want to keep it around to think about what things can I deduce from the things I've already got around. Okay, what's next? Oh, we just did that, and I just did, okay. So we're into the home stretch here, the common errors that we'll look at. There's a couple of errors that are made so frequently that logicians and philosophers have names for them. They basically have to do with messing up something that is either a modus ponens or a modus tallens argument. Attempting to do one or the other of those and getting it wrong, so really not having either of them. And as I said, these are equivalent via the contrapositive switcheroo. So yeah, you can might as well concentrate on the modus ponens, and that's where the names come from. The errors are named after the change that you would need to make to turn the major premise. Sorry, what change should you make to the major premise in order to get it into modus ponens? Create a modus ponens from it. You'd change the argument. You'd fix the error essentially by making some change to the major premise. So here's the converse error. You've got A implies B, so the setup for modus ponens, but then you have B, and in modus ponens that would be an A, and we conclude A. That's wrong, right? Here's an example of somebody thinking that all fish live in water, dolphins live in water, therefore dolphins are fish. They've got it messed up. They think this sentence that says all fish live in water means all that lives in water are fish. And that's not actually right. So if you turned the major premise around, it would be B implies A, and then, except for changing the names, you'd have the modus ponens form. The inverse error. Basically, a person who made the converse error has mistaken a conditional for its converse. Well, that's what the inverse error is too. You've made a mistake, but in this case, you've confused the statement for its inverse. So you have A implies B, and then you put down not A, and you get not B. So let's see if this example is informative. The major premise is if you install solar panels, your electric, I spelled electric wrong, your electric bill will go down. That seems like a reasonable major premise. Jim did not install solar panels, therefore his electric bill did not go down. Well, you've misunderstood the meaning of the if-then sentence in front. I mean, he could not install solar panels, but make some other change to his home, better insulation, or cost more efficient appliances or something, and still see his electric bill go down. Hell, he could just get on a really kick of turning out the lights every time he leaves a room and reduce his electric usage. You notice here that if you replace the major premise with its inverse, you get modus ponens. It's in a thin disguise, but it's modus ponens. So I took the A implies B and made it not A implies not B. Then we have not A and not B. What's the disguise? It's just that everybody's got knots on them. How would you know that these are wrong, that these deductions are improper to make? Well, you could show that it doesn't simplify to a tautology. You'd never be totally sure that you hadn't figured, maybe in that route you were just not smart enough to figure out a way for it to simplify to a tautology. The other approach is the truth table. And if you've got a critical row that doesn't have a true value for the conclusion, it's no good. It's really easy to see from a truth table. So that's the end of our slides, and I think that brings us to a great stopping point. We're at the very end of chapter 2. If you want to get a little head start, reading section 3.1 would be great, and then you'll probably have a better understanding of what I go through in the next lecture, and I hope to see you there. Well, I guess I don't see you because I'm looking at a webcam and you're seeing me, but I hope you see me there. Anyway, have a great rest of your day.